Assalamualaikum warahmatullahi wabarakatuh. Hi guys, welcome back to my YouTube channel. Okay, my name is Dea Febriana. I'm from the study of program chemistry, the Faculty of Science and Technology, the Islamic State of Raden Patah, Palembang. I'm from group 17 and course physical chemistry, lectures Jauharuddin Lutfi Aljabar MSI. Okay guys, in video I want to explain material about the phase diagram, the integration of Clapeyron equation, effect of pressure on the vapor pressure, the phase rule, and the problem of component. Okay guys, before you're watching in video, please don't forget like and subscribe. Thank you.
The phase diagram. The phase diagram shows at a glance the properties of the substance: melting point, boiling point, transition point, triple point. Every point on the phase diagram represents a state of the system. Since it describes values of T and ρ. The lines on the phase diagram divide it into regions labeled solid, liquid, and gas. If the point that describes the system falls in the solid region, the substance exists as a solid. If the point falls in the liquid region, the substance exists a liquid. If the point falls on a line such as 1, 9, the substance exists as liquid and vapor in equilibrium. The 1, 9 curve has a definite upper limit at the critical pressure and temperature. Since it is not possible to distinguish between liquid and gas above this pressure and temperature. The phase diagram for carbon dioxide. The phase diagram for carbon dioxide is shown smoothly in Fig. The solid liquid line slope slightly to the right slant. Note that liquid CO2 is not stable at pressure below 5 atm. For this reason, it is dry under ordinary atmosphere pressure. When carbon dioxide is confined to a cylinder under pressure at 25 levels Celsius, the diagram shows that if the pressure reacted 67 atm, liquid CO2 will form. Commercial cylinders of CO2 commonly contain liquid and gas in equilibrium. The pressure in the cylinder is above 67 atm at 25 levels Celsius. The phase diagram for water. Figure is the phase diagram for water under moderate pressure. This lower melting point under the pressure exerted by the weight of the skater through the knife edge of the skate blade is part of the reason that ice skating is possible. This effect, together with the heat developed by friction, combine to produce a lubricating layer of liquid water between the ice and the blade. In the connection, it is interesting to note that if the temperature is too low, the skating is not good. If water is studied under very high pressure, several crystalline modifications of ice arose. The equilibrium diagram is shown in Fig. Ice I is ordinary ice. Ice 2, 3, 4, 5, 6, 7 are modifications that are stable at high pressure. The range of pressure is shown in Fig. That the Hg and Ig curves lie only slightly above the horizontal axis. They are not shown in the figure. It is remarkable that under very high pressure, melting ice is quite. The phase diagram for sulfur. The stable form of sulfur at ordinary temperature and under 1 atm pressure is rhombic sulfur, which, if heated slowly, transforms to solid monoclinic sulfur at 95 levels Celsius. This melting point of rhombic sulfur is shown as a function of pressure. The equilibrium as rhombic equal Si is an example of a metastable equilibrium, since the line lies in the region of stability of monoclinic sulfur, shown by dotted lines in this region. Reaction S equal S mono and S liquid equal S mono. Both can occur with a decrease in Gibbs energy. The integration of the Clapeyron equation. Condensed phase gas equilibrium. For the equilibrium of a condensed phase, either solid or liquid with vapor, we have dV divided dt equal delta S divided delta V equal delta H divided T times V1 minus V2, where delta H is either the molar height of vaporization of the liquid or the molar height of sublimation of the solid, and V1 is the molar volume of the solid or liquid. In most circumstances, V1 minus V2 equal V0, and this assuming that the gas as ideal is equal RT divided rho, then the equation becomes d in rho divided dt equal delta H divided RT level 3, which is the Clausius-Clapeyron equation relating the vapor pressure of the liquid or solid to the height of vaporization, sublimation, and the temperature, integrating between limits under the additional assumption that delta H is independent of temperature yields. For substances that obey Thornton's rule, take a particular simple form which is useful for estimating the vapor pressure of a substance at any temperature T from a knowledge of the boiling point only. Effect of pressure on the vapor pressure. In the preceding discussion of the liquid-vapor equilibrium, it was implicitly assumed that the two phases were under the same pressure ρ. If by some means it is possible to keep the liquid under a pressure P and the vapor under the vapor pressure ρ, then the vapor pressure depends on P. Suppose that the liquid is confined in the container zone in the space above the liquid. The vapor is confined together with a fluid gas that is dissolved in the liquid. The vapor pressure ρ plus the pressure of the fluid gas is P. The total pressure exerted on the liquid as usual. The phase rule. The coexistence of two phases in equilibrium implies the condition, which means that the two intrinsic variables ordinarily needed to describe the state of a system are no longer independent, but are related. Because of this relation, only one intrinsic variable, either temperature or pressure, is needed to describe the state of the system. The system has one degree of freedom or is unitarian, whereas if only one phase is present, two variables are needed to describe the state, and the system has two degrees of freedom, or is bitarian if three phases are present. Two relations exist between T and ρ. These two relations determine T and ρ completely. No other information is necessary for the description of the state of the system. Such a system is invariant. It has no degrees of freedom. So the relation between the number of degrees of freedom and the number of phases present for a one-component system. The table suggests a rule relating the number of degrees of freedom. It would be helpful to have a simple rule by which we can decide how many independent variables are required for the description of the system, particularly in the study of systems in which many components and many pairs are present, and simplification of the problem is welcome. We begin by finding the total conceivable number of intrinsic variables that will be needed to describe the state of the system containing C component and P phase. These are listed in each equation that connect this variable implication that one. The problem of component. The number of components in a system is defined as the case number of chemically independent species that is required to describe the composition of every phase in the system. At first value, the definition seems simple enough, and in ordinary practice, it is simple. A number of examples will show up the joker in the deck that little phase chemically independent. Example: the system contains species PCl3, PCl 5Cl2. There are three species present but only two components because the equilibrium PCl3 equal PCl5 plus Cl2 is established. In this system, one can alter the number of mole of any two of their chemical individuals arbitrarily. The alteration in the number of mole of the third species is then fixed by the equilibrium condition. Consequently, any two of these species are chemically independent. The truth is not three are only two components. It is clear that an accurate estimate of the number of components in a system presupposes some experimental knowledge of the system. This is an unavoidable pitfall in the use of the base rule. Failure the relax that an assumed the equilibrium has been established in a system sometimes leads an investigator to rediscover the hard way the second law of thermodynamics.
Okay guys, thank you for watching until the end. I hope you can understand what I'm saying. Sorry if in my delivery there are wrong because I'm still learning. Please understand. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.